Hi everybody, welcome to a quick video on the development of the kinematic equations. So the kinematic equations are equations that we can use to help, they have to do with the motion of objects. So the purpose of this video is to show, we've been using a lot of graphs and everything to model the motion of objects. But while graphs are great and we can pull a lot of good information, they do take time to create. And what we're going to do is show that there's mathematical equations that we can use instead of the graphs. The equations come from the graphs, but sometimes they're a little bit quicker and a little bit easier to use if we're just solving for like a certain value, if we're solving for something really quick and don't want to have to create a whole graph. So in the end, this video is meant to show the connection between the mathematical equations and the graphs that we get them from. So to start off with an example, we have a velocity time graph. There's an object. What do we know about this object? We know it's moving in the positive direction because it has a positive velocity. We know that it is speeding up because the direction of the line is upwards towards bigger velocity numbers. We know that the initial velocity is 5 meters per second. That's our y-intercept. The final velocity of the object is 20 meters per second. And to find the acceleration of this object, we know that the acceleration, or the rate at which velocity changes, is just the slope of the velocity time graph. So I can take my rise, that's my change in velocity, or 20 minus 5. And my run is the time, which is should say 30 seconds here. Does not, says 15. That's an error. Should say 30 seconds here, which will get you 0.5 meters per second squared. Oh well. Next is the equation. So we can also find the equation line for this object. We know that we've done this for position time graph. Now we can do it for a velocity time graph. So for this line, we start with our y-intercept form, y equals mx plus b. And we're going to substitute in physics variables. So my slope, we know, is equal to the acceleration. On the x-axis is time, so I'll plug in t. My y-intercept is the initial velocity. We already talked about that. And finally, on the y-axis is the velocity at a certain time, which I'm going to plug in as the final velocity, vf here. So we come up with, this is, right here in the box, this is a general equation. This works for any object. Any object that has a velocity time graph like this, that has a constant acceleration, we can use this equation. And then if we want to be more specific for this specific graph, we can plug in what the acceleration is and what the initial velocity is. So this works for anything. This works for this specific graph. So there's one equation that we developed from the graphs. Another thing, velocity time graph. We've said that we can't find where the object is, but can we find how far the object has traveled? If we know its velocity and we know how long it was traveling, there should be a way where we can see its displacement or its overall change in position. But how can we find this? I don't know. We haven't talked about this at all. We can find it. There is there's a shortcut that works out pretty well with velocity time graphs. Turns out that displacement is equal to area underneath the graph. Now, what do I mean by that? There's a line. Here's our motion of the line in black right here. The area underneath the graph is this, what's shaded in orange. So it's all the area between the line and our time axis here. If I find what that area is, that gives me what the displacement of the object is. Kind of a neat trick. So let's work through an example. If I want to find this area, it's a trapezoid or something. Not really sure what the shape is. But it doesn't matter because I could break it down into two easier shapes, a triangle and a rectangle on the bottom. So the triangle, the area of the triangle is equal to 1/2 base of the triangle times height of the triangle. The area of the rectangle is equal to base of the triangle times the height of the triangle. And now I can plug in numbers. I can go through here. My base of the triangle is the time. This is the height of my triangle, so 20 minus 5. The base of the rectangle is 30. The height of the triangle is 5. Plug all of that in, and I get 375 meters for displacement, which is cool. Works for this graph specifically. I know that from 0 to 30 seconds, this object moves 375 meters. But what happens if I just wanted to use this information more generally, just kind of a general equation that I could use instead of having to go to the graph every single time? Let's see if we can take this, excuse me, take this equation and just put in the general physics variables. So we start off, again, displacement is equal to the area of the triangle plus the area of the rectangle, area of the triangle, area of the rectangle. But instead of plugging in numbers, I'm going to plug in the variables that correspond to these different heights and bases. So, for instance, for the triangle, we know that it's 1/2 times the base of the triangle. Well, the base of the triangle is equal to this time interval, okay, or 30 seconds. So this would be time. The height of the triangle is going to be equal to my final velocity minus the initial velocity. The height of the rectangle, the base of the rectangle is always going to be equal to the time. The height of the rectangle is always going to be equal to the initial velocity. So if I go from 0 to 5, my initial velocity is 5, and that's equal to the height of the rectangle. So there you go. There's the equation using all the variables variables instead of the numbers to plug in here. This is not the form that you'll typically see the equation in. Typically, people will take the other equation that we had and rearrange it a little bit and plug this in. So they'll take VF minus VI and substitute it with A times T. And the final form of the equation that we're going to use in class is our classic equation down here, that displacement is equal to 1/2 times the acceleration times time squared plus initial velocity times time. So there you have it. If you're asked for the displacement of the object and you're given this information, you're welcome to build a velocity time graph and find the area underneath it. But if you don't want to go through all that work, you have the information, you're welcome to use this equation. It's kind of like a guess method problem to solve for it a little bit quicker. So we showed how to develop different equations from the graphical models. So this is one equation we can use right here, VF equals VI plus AT. That was the first one we developed. The second one we developed was the one I'm circling right now. These other two, I didn't show how to develop those equations. You could just take my word for them that they're legit and they work and we can use them. So now when you're given information on an object and you're asked to solve for something, you could go to and create a velocity time graph or position time graph, whatever you feel like you need to solve for it. But as a shortcut, you can alternatively come to these equations, plug it into guess method, and solve for your answer. Over here are just the variables, just in case you forgot what any of the variables stand for or what their units are. Just kind of a reminder over there. So we'll talk about this more in class. Thanks for watching. Bye. Exit.